Hello everybody, welcome back to this course on Internet Technologies. I'm Vardan and today's lesson is all about IP version 6. So IPv4 was designed in the early days of the internet when no one anticipated how massive and device packed the modern internet would have become. With just 32-bit addresses, IPv4 supports around 4.3 billion unique addresses. Now, that may have seemed plenty back then, but with billions of smartphones, laptops, IoT devices, and servers today, we quickly ran out. Another issue is IPv4's two-level addressing scheme, where an address is divided into a network part and a host part. While simple, it's inefficient for large hierarchical routing systems. Moreover, IPv4 struggles to support real-time applications like voice, video, or gaming, which require stable and consistent routes for quality service. And lastly, routing tables in core internet have grown so large under IPv4 that it has strained both the capacity and performance of backbone routers. These problems laid the foundation for the creation of IPv6. Even though IPv6 is a significant upgrade, it still preserves the core characteristics of IPv4. Both are connectionless protocols, meaning there's no dedicated connection or session established before data packets are sent. Each packet is independent and might take a different route to reach its destination. They also both use a maximum hop count called TTL in IPv4 and hop limit in IPv6, which prevents a packet from circulating endlessly in case of routing loops. The delivery model remains best effort, so there's no guarantee that a packet will reach its destination, nor any inbuilt recovery mechanism in the IP layer. Lastly, while both protocols can handle fragmentation, IPv6 shifts this responsibility to the source, with routers no longer fragmenting packets midway, handling via an extension header. So, at the core, IPv4 and IPv6 remain similar in operational philosophy. So IPv6 was designed not just to solve IPv4's problems, but to future-proof internet addressing for decades to come. It uses a 128-bit address format, giving us around 3.4 into 10 raised to the power 38 possible addresses. To put it in perspective, that's about 6 into 10 raised to the power 23 addresses for every square meter of Earth's surface. And IPv6 uses a streamlined header structure, a fixed length based header followed by optional extension headers for additional functionality. A key feature is the flow label, allowing devices to request high quality, stable paths for real time services like video calls and gaming. IPv6 also brings addressing flexibility, making it easier to assign dynamic IP addresses, and introduces anycast addressing where multiple devices share an address and the network automatically routes packets to the nearest one. This is especially useful for things like mirrored web servers. So IPv6 is about scalability, simplicity, and smarter networking. Let's look at the structure of an IPv6 datagram. At the very front is the base header, a fixed 40-byte section that carries essential routing information. Immediately after that comes extension header. These extension headers are optional headers that provide features like routing fragmentation, security, or quality of service. The beauty here is modularity. Unlike IPv4, which tried to pack everything into a single header, IPv6 keeps its base header clean and offloads these extras to these optional extensions. After extension headers comes the transport layer PDU, which might be a TCP segment, a UDP datagram, or a data from another transport layer protocol. This clean layered structure makes IPv6 faster to process, more flexible, and better suited to modern networking demands. Breaking down the base header fields, version simply identifies this as an IPv6 packet. Traffic class works much like the type of service field in IPv4. It lets us prioritize traffic. So a video call can be treated as a higher priority than email. Flow label is a unique identifier for real-time traffic flows. Think of it as tagging packets from a video call or a voice over IP session, allowing routers to recognize and treat them as a continuous stream. Payload length specifies the length of the payload, meaning everything after the base header, including extension headers and the transport layer data. Together, these fields allow IPv6 to manage traffic types, improve quality service, and optimize data handling on a larger scale. Next, we have two crucial fields. Next header. This field is like a pointer. It tells the system what comes after the current header, whether it's an extension header or a transport protocol like TCP or UDP. It essentially links headers together in a linked list fashion, giving IPv6 incredible flexibility without bloating the base header. Hop limit works like the time to live in IPv4. Every time a packet crosses a router, this value is reduced by 1. When it hits 0, the packet is discarded. This prevents infinite loops in the network and keeps traffic flowing efficiently. One of the most powerful features in IPv6 is its extension headers. Some of the common ones are routing header, which allows source routing, where the sender specifies the path the packet should take. Hop by hop options header is processed by every router along the packet's path. This is useful for network diagnostics or special signaling. Fragment header is something that in IPv6 only the source device fragments packets. Routers don't do it mid route. The fragment header helps in reassembling data at the destination. There are other extension headers for things like security, mobility, and authentication, and their modular nature makes IPv6 incredibly flexible and future ready. IPv6 addresses are represented in a colon hexadecimal notation, that is 8 groups of 4 hexadecimal digits separated by colons. There's no fixed address class system like IPv4. Instead, IPv6 uses prefix length to indicate how many leftmost bits represent the network portion. For example, /64 or /48, something like CIDR. There are three main address types: unicast for one-to-one communication, multicast one-to-many communication, anycast is one to nearest. That is, multiple devices share an address, but network routes the packet to the nearest one based on topology. This flexible addressing system is one of the core improvements over IPv4. Now, IPv6 addresses aren't just long, they're highly structured for efficient, scalable routing. A typical global unicast IPv6 address begins with three fixed bits 001, indicating it's globally routable. Then comes global routing prefix, usually 45 bits long. It's assigned to the internet service providers by regional internet registries like APNIC or ARIN. Next, the subnet ID. It's a 16-bit field and it's managed internally by organization. It lets them subdivide their assigned address blocks into up to 65,536 subnets, enough for even huge enterprises. Finally, the interface ID, a 64-bit portion, identifies individual devices on the subnet. it can be auto-generated from the device's MAC address using EUI64 format or assigned randomly for privacy. This hierarchical structure allows ISPs to announce a single prefix to the internet, massively shrinking routing tables while organizations enjoy tremendous internal flexibility. And since the interface ID is always 64 bits, IPv6 can seamlessly support stateless address auto configuration, where devices automatically generate their own addresses without needing a DHCP server. So with that, we've come to the end of this lesson, and in the next one, we'll get started with common internet applications and learn about some client server concepts. So thank you for joining in, and I'll see you next time.